Kia ora. In this video, we're going to look at a few examples of L'Hopital's rule. We're not going to do necessarily bog standard problems, but we're going to do a few examples that illustrate some of the quirks that can come up when you're looking at these problems. So the first one we're going to do is the limit as t goes to 0 of 8 to the t minus 5 to the t, all divided by t. Okay, so remember with L'Hopital's rule, what we're looking for is a situation where as we approach the limit value of 0 in this case, our fraction goes to either 0 divided by 0 or infinity divided by infinity. These are what we call indeterminate forms. And if it's going to one of those cases, then we, with a bit of luck, we'll be able to use L'Hopital's rule to find the limit. So here, we can see that 8 to the t, as t goes to 0, anything to the power of 0 goes to 1. So both of those pieces on the top are both heading towards 1. And the bottom is going towards 0. So we get a 1 minus 1, which is 0, divided by 0 situation here. So for L'Hopital's rule to apply, a couple of technical conditions that need to hold. One is that we can differentiate the top and the bottom of the fraction. And the other is that as we move away from 0, or from the limit point here, the thing on the bottom of the fraction doesn't stay at 0, which it doesn't. Okay, so L'Hopital's rule says that so long as everything is nice and we can differentiate the top and the bottom, we can solve this limit, or find this limit, by instead taking the limit of the ratio of the derivatives. So basically I'm going to differentiate the top of the fraction and differentiate the bottom of the fraction, and then that will be the same limit. It's not the quotient rule, I'm not differentiating the fraction as a whole, I'm differentiating the numerator and the denominator separately. Now if you're anything like me, you might have been thrown by how on earth do I differentiate 8, for example 8 to the power of t. So let's just make a little working space down the side here. Just a little note, if you want to differentiate something 8 to the power of t that's not e, the one we know how to do is e to the t, right? E to the t differentiates to e to the t. But what do we do when there's some other number? Maybe you've forgotten. The trick here is that we turn it into a natural exponential instead of using 8. So what we do is we just take advantage of the fact that this is the same as dt of e to the log of 8 to the t. Remembering e to the log at inverses, so that's just transforming it in a special way. And that equals basically, well, we can, the derivative of e to the t log 8, and now it's just e to the t times a constant, so that would just be log 8 e to the t log 8, and if we take it back to how it was before, then that turns into log 8 of 8 to the t. So when we're differentiating, we just need to bring that factor of log 8 out the front. So what we can do here, L'Hopital's rule says that this will be equal to the limit as t goes to 0. On the top, 8 to the t goes to log 8, 8 to the t, minus log 5, same logic, 5 to the t, divided by 1. Now 8 to the t is going to go to 1, 5 to the t is going to go to 1 as well as t goes to 0. So these bits both go to 1. So what we're going to do is just basically substitute in now, and that will give us log 8 minus log 5. Okay, that came out nicely. Alright, for our next example, we'll do one that looks maybe a little bit less like L'Hopital's rule at first glance. So this one is going to be the limit as x goes to infinity of x minus log x. Okay, so this one hasn't been presented to us as a fraction. Instead we've got two things, both of which are going to infinity. So we know that x goes to infinity as we head towards infinity. And we know that log x also goes to infinity as x goes towards infinity. So we've got basically a competition here. Which one is going to get to infinity fastest, or are they going to go about the same rate? We can get any number of different possibilities here, but this is kind of an indeterminate form that looks more like infinity minus infinity, and we want to untangle what happens here. Now, when you get this situation, there are two kind of things you might consider doing. If there are fractions involved, you might see if you can turn it into a single fraction. Sometimes that fraction will then be a 0 over 0 or an infinity over infinity. There is no fraction here, so that's not really going to work in this case. The other thing you can try and do is take some kind of common factor out and see what happens. So here, what I'm going to do is I'm going to take that factor of x outside. This is a little bit of a leap perhaps, but this kind of trick will often work. We suspect that x is going to, if we just visualize the graphs, we know that x goes off like this, and log x is kind of going like that. So we kind of expect that x is going to win, and we kind of think in advance that this answer might actually just be infinity, because this distance between these two things is going to get bigger and bigger as x gets large. So what I'm going to do is I'm going to take a factor of x out the front and then see what I get inside. So this is going to be 1, and this term is going to be log x divided by x. Right, so what we have here is now x times this thing here, which we can consider separately. So if I look at the limit as x goes to, let's just look at the log x over x piece. That's going to be, now this is of the form infinity over infinity. And this one, I can use L'Hopital's rule to solve it. So it's going to, derivative of log x is 1 over x, derivative of x is 1. The piece on top, that goes to 0. And the piece on the bottom goes to 1, obviously, and so that limit there is just equal to 0 over 1, or just 0. So just this once, I'm going to remember when we've got limits of things multiplied together, we can take the limits separately. So I'll spell it out in full this time, and I may not in the next example. So that equals the limit as x goes to infinity of x times the limit as x goes to infinity of everything else, 1 minus log x over x. So what we've seen is that this piece over here is just 0. So this overall piece here is going to equals 1. And this bit, as x goes to infinity, this bit goes to infinity. So overall, that's going to give us the limit of infinity, as we kind of expected was going to happen in the first place. All right, now we're going to do one more example. The last one is going to be quite involved because it's going to use lots of different techniques that you might come across when you're doing L'Hopital's rule problems. So don't worry if this one seems a little bit advanced. It's kind of a good way of covering most of the remaining sort of tricks that you're going to have to know how to do. So this last one we've got is the limit as x goes to infinity of tan 2x all to the power of x. All right. Now, when we have so this one, let's just have a think about what happens to infinity. Not infinity, sorry, it's going to 0 from the right. Tan 2x over x. So just have a think about what happens here. Tan 2x, as we go towards 0, is going to head towards 0. And the x is heading towards 0. So this is an indeterminate form, basically of 0 to the 0 as we approach the limit. So once again, L'Hopital's rule can be used for these problems, but not straight away. We have to do a little bit of work first. So the trick with these ones is going to be to let y, another variable, be our thing that we care about, tan 2x all to the power of x. And then what we do is we take the logarithm of that. That equals x log of tan 2x. And we find the limit as x goes to 0 plus of log y first. And then we can turn that into the limit as x goes to 0 of y afterwards. This is going to be our strategy. All right, so let's get to it. So the limit, so the log y was equal to x log 10x. So we want to find limit as x goes to 0 plus of log y equals the limit as x goes to 0 from the right of x log tan 2x. And just think about how this behaves. This is going to 0 and tan is going to 0, so log of that is going to negative infinity. So now we have a indeterminate form which is 0 times infinity. And again, we don't know which of those is going to win. So when we have that situation, what we know, when we've got a product, a 0 times infinity, then what we normally do is we try and turn it into a fraction. So if we've got, if this is f times g over here being 0 and infinity, then one thing you might do is you might turn f times g into either f over 1 over g, it's the same thing, or g over 1 over f. So that one would, the first one, if it was, that would be a 0 over 0, and this form would be infinity over infinity. Sometimes you end up trying both. One of them is really easy, one of them is really hard. Generally speaking, if there's a log involved, you probably want that to be the one on top, just because it gets quite messy otherwise. So what I'm going to do is I'm going to turn this into the limit as x goes to 0 from the right of log of tan 2x divided by 1 over x. And this is now, as I'm just reminding myself, tan goes to 0, so log of that goes to infinity. So this is now of the form infinity over infinity. That's the indeterminate form we have here. Okay, so we can now use L'Hopital's rule. Both of those things are differentiable, so long as we stay on the positive side of 0, which we are doing, so that's fine. So this equals the limit as x tends to 0 plus, this time I'm just going to do my derivative straight away. So let's see, log of tan 2x goes to 1 over tan 2x times the derivative of tan 2x, which is 2 sec squared 2x, all divided by derivative of 1 over x is negative 1 over x squared. Okay, and let's just turn that into a single fraction before we do any more tidying. So that equals the limit as x goes to 0 plus of negative 2 sec squared 2x times x squared, all divided by tan 2x. Okay. Right, now what do we do with this? So we actually have a piece that we know how it behaves in what we've got here. If I were to consider just sec squared by itself, remember sec is just 1 over cos, and cosine is going to 1 as x goes to 0. So that means that the sec squared piece is also just going to be heading towards 1. So what I can do is I can basically take that part of the limit out separately. So that equals, and again I'll spell it out in full just to be clear about what I'm doing. This is the limits product law. I can take the sec squared piece out the front that I know is going to go to 1 times the limit as x goes to 0 plus of negative 2 x squared over tan 2x. Okay, so that's interesting. So the first part of that product, the limit here, that's just going to be equal to 1. So I can just kind of forget about that now, because it's just going to be, so we're going to make it one more line, equals the limit as x goes to 0 from the right of negative 2x squared over tan 2x. And that is because this piece equals 1. So we've just sort of got rid of a term that we know how it behaves, so we can just ignore it, and we can just focus in on this. And again, this is a 0 divided by 0 situation, so we're going to have to apply L'Hopital's rule one more time. Well, maybe one more time, maybe even more than once, but we'll just keep on going. So again, I'm going to differentiate the top and the bottom. So the top is going to go to negative 4x, and the bottom is going to go to 2 sec squared 2x. Okay, now I finally have things that behave differently. So on the top, that 4x is going to go to 0, and on the bottom of my fraction, this piece overall is going to go to 2. So actually overall, this limit is going to equal 0. But we're not finished, okay? So we've done a lot of steps, so we kind of forgot what the problem was. But if we go back, we just found the limit as x goes to 0 of log y. But the thing we actually want is the limit as x goes to 0 of y. So let's just finish the problem off just to the right there. Of log y equals 0. And so as x goes to 0 plus of y, which is the thing that we care about, is equal to, basically we can take the exponential to undo the log outside of the limit. So that is going to equal e to the limit as x goes to 0 plus of log y, which is equal to e to the 0, which is equal to 1. Right, and that is the answer, hopefully, if we've done everything correct, that the overall limit should equal 1. And sometimes when you're dealing with these limit problems, you might be worried you've made a mistake, and you might want to sort of somehow sanity check that you've done this right. So one way to do this is just to literally go to a computer and type in your function and see, or calculator, and see what happens as we get close to the value in question. So I'm going to jump across to the computer now. And I am going to put my function right back to the start, so I'm just going to scroll back up. My function is f of x is equal to tan of 2x all to the power of x. This is a programming language called Julia. It's a bit like Python or MATLAB or whatever, but it does what we want. And I just wanted to know what was going to happen to this as I headed towards 0 from the right. So just to sanity check that my answer of 1 was correct, let's try put in some values of our function as we head towards 0. So f of 0.1 is 0.85. Let's get a bit closer to 0 from the right, so it's positive. And you can do this for any limit problems for trying to understand how things are behaving. Getting closer to 1, I'm pretty sure that this is going to be correct. Let's just do a couple more zeros. And you can see that does definitely appear to be tending towards 1. Okay, so that's enough for now. We'll see you next time. Ka kite anō.